To simulate physical reality effectively, a machine learning model needs to represent it compositionally. That means taking a massive physical system, like a chaotic rigid body collision, and breaking it down into distinct interacting subsystems across space and time. The test for this is strict mathematical compositionality. If a model encodes two separate physical subsystems into latent vectors and combines them, the resulting vector must be identical to the embedding produced by directly encoding the combined physical union from the start. A recent paper puts this to the test using a contained two-dimensional environment. The simulation tracks 64 interacting particles, drawn from rigid objects like circles and rectangles, undergoing gravity and elastic collisions. The authors propose that a continuous, learned neural latent space can be trained to strictly obey discrete algebraic rules without relying on rigid hand-coded architectures. The proposed architecture pipeline consists of three main components: a translation invariant graph encoder to represent the particles, a symmetric combine operator to merge subsets, and a spatial density decoder to project the latent representation back into a visible grid. If a neural representation can be strictly closed under spatial composition and time evolution, models can move past merely mimicking pixel-level simulations and begin performing hierarchical physical reasoning across vastly different scales. Before testing the algebra, the system has to successfully decode the spatial density from the latent space back into a physical representation. Early iterations of the decoder stalled at a hard limit. No matter how much capacity was added to the neural network, the density reconstruction error plateaued at a root mean square error of roughly 0.190. A primitive constant predictor that simply output the dataset's mean density at every step actually achieved a better error rate than the complex neural network. Standard pixel mean squared error evaluates spatial density locally. Placing mass 1 pixel away incurs the exact same penalty as placing it across the grid, ignoring physical distance. To avoid massive penalties for slight misalignments, the network simply smears mass uniformly. Pixel MSE actively punishes spatial sharpness in favor of diffusion. It is structurally unsuited for high-fidelity physical decoding. To fix this, the authors replace the MSE penalty with a sliced-Wasserstein 1 distance, an approach rooted in optimal transport theory. Sliced-Wasserstein projects the two-dimensional density grid's mass onto uniform one-dimensional directional lines. The loss measures the gap between the cumulative distribution functions of target and prediction. Now, mass in the wrong location incurs a penalty strictly proportional to its physical distance. Implementing this loss function entirely eliminates the smearing pathology. The density error drops from 0.190 down to 0.114 at a fixed architecture capacity. That figure breaks below the theoretical oracle ceiling of previous MSE-based models. Independent linear probes applied to the resulting embedding accurately predicted 8 completely held-out physical observables, achieving R-squared values of 0.89 or higher. By utilizing optimal transport, the network inherently respects physical distance. This establishes the baseline spatial accuracy required to attempt a compositional latent algebra. With spatial decoding resolved, the next challenge is training the symmetric combine operator to be associative, even though neural networks naturally produce approximate outputs. The system enforces this behavior by applying a central training constraint called path independence. A full scene splits into a hierarchical decomposition tree, is encoded individually, and combined bottom-up. An anchor loss ensures this final combined latent vector mathematically matches the single vector produced by directly encoding the full 64-particle set at once. A complementary dispersion penalty ensures that completely random tree partitions of the exact same data also converge on identical vectors. Associativity here is not a pre-programmed structural absolute. It is a highly constrained geometric behavior explicitly hammered into the latent space through path independence. The ultimate test of the system takes 4 entirely separate 64-particle scenes and forces them through 2 drastically different mathematical combination paths. The balanced tree composition merges block A with B, block C with D, and combines those intermediate results to form a 256-particle representation. The second path, the chain tree composition, takes block A, sequentially absorbs B, then absorbs C, and finally absorbs D. These 2 highly divergent paths produce final latent embeddings that agree to within a mean squared error of 0.32 and output spatial densities that differ by an error of less than 0.001. The symmetric combine operator functions as a true associative monoid in distribution. A learned latent algebra can exist for physical systems. The system does have a strict breaking point, the boundary of the encoder's trained spatial priors. Directly encoding a 128-particle scene using the model trained purely on 64-particle sets degrades performance by roughly 65%. This bottleneck critically impairs the algebra. Combining two 64-particle scenes forces the network to generate an out-of-distribution 128-particle latent vector that it has never been optimized to decode. Multi-size training is currently being developed to address this coverage gap, but it highlights an architectural dependency. The latent algebra is entirely bottlenecked by the spatial generalizability of its encoder. While strict limits on scale remain, pixel MSE is demonstrably obsolete for spatial decoding. Forcing a continuous latent space to reliably act as a discrete compositional algebra is now a completely verifiable reality.